beginning of this location that I know, which is usually the beginning of my pipe, or it might be the beginning of or reroute of my pipe, it might be at a station, but it's usually a location that I know. From here, I go a certain distance to get to something. I go my 500 feet to get to my valve. But in my pipeline, I might have breaks. So I might have a pipeline that's 1,000 feet long. In the middle of it is a station. But I call it one pipeline. So I'm going to start at the beginning at 0, and I'm going to go 500 feet to that station. But then I'm going to go another 500 feet to the end of my pipeline. And I might start over at 0 again. Because, the guys in the field, the engineers who laid the pipe, they started at 0 when they put that in. So I have to remember that at that station, I'm starting at 0, not 500 or 500 to 1. So now, in the database, I need a way to store both of these. I have to store the first 500 feet and the second 500 feet. But now I have kind of a weird abstraction problem. Now I have to be able to say, well, how do I uniquely identify the difference between those two things? If I have a valve at 550 feet on the first part, and a valve at 550 feet on the second part, how do I know the difference between those location files? So what we do is we have this thing we call measure. We may lay measure on top of the whole route. So now I have 1,000 feet of measure. I'm going to start at 0. My first valve is going to be at still 550 feet of measure. But then my second valve, which was at 550 stationing on the second part of my line, is now going to be, was at 50 feet. I'm sorry, I'm using the wrong numbers. I'm sorry, I'm getting confused. It was at 50 feet, is now going to be at 550 feet measure. Okay, so I'm building a unique location identifier, basically. I'm extracting that stationing and converting it to measure. This is kind of complicated. Did you do that?
Yeah,
you want to
add on? So I think it's worthwhile to say that that's not an easy concept. But it's important to take away that that's really the heart and soul of the PODS database. And you need to take the time to understand that concept. we're not expecting you, after that really good, actually, overview of it. It's better done with a whiteboard where you can draw it out. Because it is really a highly visual aspect. But it's complicated. It's part of the deal. That's just the way it is. And we can't start, and really it takes a good day to sit down and really have people understand the concepts. I want to make one addition to that. PODS is designed to work in a database alone. It does not need a GIS. It is not designed. It is designed to work with GIS. It is not dependent on a particular GIS. It's supposed to be agnostic to how you implement the spatial representation of the data. Okay, so that's an important takeaway for that. Okay, it is designed to work with any GIS system. And when I went back to the abstraction thing, everything was in tables. Everything is in tables, and from those tables, if you do it correctly, you should be able to build the spatial features in a GIS and show it. All right, so that's an important takeaway. Okay, so one of the things that you will hear in the industry is about the ArcGIS pipeline data model. Okay, it was designed particularly as a geodatabase for pipeline systems in the ESRI geodatabase. Okay, it is built for ESRI. It's using the geodatabase. Those are ESRI is a software vendor. They make ArcGIS, and the geodatabase is their construct. They're a way of enhancing a database to store geographic information. APDM was designed as a template. Okay, for people who think abstractly, okay, and look at, I only want to implement what I want to implement. APDM was designed that way. You take your set of core tables and you add to it. All right, and it describes and handles stationing in a similar manner to PODS. Okay, it contains a set of conceptual features as an example. Where it differs, okay, from PODS is that PODS, okay, first of all, is RDBMS and GIS independent, as we said before. Okay, it is a very extensive data model. When you look at that entity relationship poster over there, I think that's probably only showing a quarter of all the tables that are involved in the model. It's very comprehensive. Okay, APDM was a grassroots effort. It was sort of fostered by ESRI because it was involved with their technology, but there's no sort of real official organization anymore. PODS has obviously a viable organization. We have a paid position in the executive director managing the continuance of the model. As you can see from this conference, it's completely sold out, so there's a lot of community interest. And it is an organization as well as the data model itself. We do support pretty much any DBMS, although most of the effort is put to Oracle and SQL Server. Do we write SQL for other things?
That's not any RDMS, that's Oracle SQL Server.
Never mind. And right now, one of the concurrent presentation going on with us is the open spatial effort to support using SQL Server and Oracle's native data types, spatial data types. Brief overview of the history of the model. So since 1998 to 2005 and beyond, we've gone through the evolution of the model. The one thing I want you to take away from this, there's a lot of information, is if you look 1998 to 2012, if I have my math right, that's 14, right? Yeah. Okay. 14 years of existence in the industry, perpetuating and growing the model. It's a stable organization and platform for doing that. Okay, so let's look at the data model itself and the idea of a system. Okay, everything in the pipeline world usually can be broken down into a concept of hierarchy. Okay, and a hierarchy starts with a higher level object or grouping and breaks it down. And PODS models the highest level of a pipeline system or a company or organization as a system within the model. And you notice here, this drawing shows you the fact that it can support not only midstream transmission, but also gathering and exploration, and I think theoretically it could even do distribution at this point, because it's just systems within systems. So PODS breaks down all of its data hierarchically. Here's my pipeline system. Here are the companies within my system. Here are the lines within my system. And as Christopher used in his example, this one line could have two routes, the route into the site and the route out of the site. How do we incorporate sites? Okay, a site can be what you see as a site, maybe an offshore platform or a valve station or the junction of pipeline systems or maybe even a meter site. Okay, so PODS is organized and built to support this hierarchical organization of information. Theoretically, you don't really even need to put pipes into a PODS system. You can just have systems, lines, routes, stations, sites, and you've described your pipeline system. And you could, if you filled out coordinate and geometry tables, then build that in a GIS and show it spatially and say, here's my pipeline system. Completely agnostic. I'm not tracking any other data than that at this point, which, for the example of using it for an exploration thing, here's my proposed pipeline. And PODS is completely able to do that, and it organizes the data totally hierarchically.
Okay, so now we're going to talk about parts of the actual model that you'll see on the ERDs and that you'll see in PODS 6 if you stick around and watch P9 talks more. So the most important part of the model and the only submodule that you have to have in PODS 6 is the core. Here we're calling it the center line. So we have our station center line. We have a line, which is just a grouping of pipelines. It doesn't have anything associated with it other than it has a name, and it's a group of pipelines. So it could be a system, it could be a region, it could be a team. You can divide it up however you feel. Below that, we have a route. And the route is the first physical entity that we're trying to abstract and describe. So the route is our actual pipeline. A route has measure in it, and a route will have multiple series within that. And that's where our linear referencing comes in. So a route is that big piece that went our 1,000 feet, and in a series which hangs below it here in the model is that first 500 and then that second 500. That makes any sense to anybody. And below that, technically speaking, then we have to start storing all of that linear referencing information. So hanging below that, we have what we call the station point table, which is where we stick all of those stations and measures. And below that, we have the event range table. And the event range is where all of the features that go onto my pipeline attach. So that's one of the strengths of PODS, and one way we're able to make it so modular is by having that event range table, and you can kind of add new features onto your pipeline very simply. So once you have that kind of hierarchy described, you have to have a location. So Pete talked about you can describe your entire pipeline without knowing where it is on the earth. And PODS allows you to do that because you don't have to populate the quote-unquote GIS part of it. You could just describe your entire pipeline in linear referencing terms, and you don't care where it is, whether it's going out over a mountain or not. You're just describing that pipe. So then you want to describe where it is. So we have the location part of this. And so when we have location, we have coordinates. The coordinates are associated with station and measure values on our routes. So everything kind of ties through linear referencing, and this is one of the big deals why we have to have station and measure in PODS. Yes, we do. Everything, the center line, the geometry, everything is tied through that linear referencing in PODS right now. And the rest of that are just a bunch of helper tables that go along with coordinate. It's not important that you necessarily understand the use of every one, but it's just kind of important that you understand the concept that those are helper tables that describe that coordinate. Where did it come from? What's its accuracy? What did I do with it? That kind of stuff.
Pipeline facilities are what we're calling product transport. They actually are pressurized and they transport product, whether it be liquid or gas, doesn't matter. So there's a wide variety of things, but if you imagine anything with a diameter that can pass gas, that's in this one. Geographic features, again, PODS is GIS agnostic. It should be apparent to you with the total ubiquity of spatial data out there that you would store a lot of your land-based information. But again, with Christopher's example, you could take your hierarchy, your central line, without having any coordinate information, put this data into your database, and attach geographic features to it. You just know that they happen at a particular interval along the pipeline. They happen at a measure from the start of the pipeline. And if I happen to know what that is, be it a mile post measure, or a kilometer post, a meter, or footage, or change, whatever, you can store these information. So geographic features are the description of the high-level geographic objects that you typically run into, run over, or pass by. Rust never sleeps. So you methodically protect your pipeline, again, without getting into the science of it, just a whole bunch of tables that describe protecting, running a current to mitigate the effects of corrosion, both internal and external on your pipeline. And I think another important one is the idea of sites. These are stations, locations, terminals, platforms, manifolds, subsea tie-ins, rectifier stations, anything that involves facilities that you own that you want to manage. And if you think about it, go back to my point about the enterprise, the idea of knowing site and line, when you're tracking plant and accounting codes and you're integrating with Maximo and SAP, okay, you want to be able to have these features in your GIS, know where they are, and tie them to those other systems. Okay, come up with 100 things you want to ask your GIS, and I guarantee one of them, driven by one of your business people, is what's the maintenance history on that? When's the last time I inspected it? Why did it break down? Last one, again, just highly detailed, is the whole idea of within a site, a whole bunch of tables describing compression. Again, you don't need to use all of these. They're in your data model. Modularization now, in our next presentation, will give you the option to include it or not, which is actually quite powerful. Here are the standard modules usually we need to do. So, I mean, I wouldn't let, base your noodle on all of this stuff other than just going to give you a high level overview of what's in the data model.
Okay, so physical inspection. So if I'm going to go out and I do a physical inspection of something, whether it's a person or it's a device or it's a reading, whatever it is, there's a whole set of tables in here to store the results of those physical inspections. Cathodic protection inspections, again, part of physical inspections, but cathodic protection. Inline inspections. And boy, is this a hot topic. So, inline inspections. So we have this thing we send through the pipeline and get a whole lot of data back, and now we got to store it somewhere. So that's what these tables are for. We're getting a lot of feedback saying that maybe they're not working in the real world. I'm not going to get into that now, but we are going to look at this. So inline inspections. Close interval surveys, we can go along and stick a hole in the ground. place to store it in pods. SCC potential, place to store it in pods. Weak. Hope these are